Well, hello and welcome again to our journey into number theory, and in particular analytic number theory. And in this section 6, we're going to have a bit of an investigation of the very famous prime number theorem. This was guessed by Gauss, as I've mentioned before, at a fairly early age, that the number of primes less or equal to x is asymptotic to x on log x. So we're going to go through essentially a proof of this. There are quite a number of proofs to this, and I'll mention one of the more recent ones, the one by Newman. We're going to have a look at a sort of a modified version of the one by Ingham here. So this section will be devoted to studying the proof of the prime number theorem using analytic methods. You'll be aware that in 1945 Selberg and Erdős independently found so-called elementary proofs of the prime number theorem, and it's a wonderful example of where the word elementary as it's used in mathematics is very different to the word elementary used elsewhere, because the proof is by no means elementary. It's very clever and quite sophisticated, but it doesn't use analytic methods. It doesn't use integrals or complex analysis or anything. And the starting point for that is the so-called Selberg identity that we did mention in one of the earlier, in fact I think we proved this in one of the earlier videos, where this capital lambda of x is our von Mangold function we've defined before, and this psi of x is the partial sums of the von Mangold function. The other known proofs are all analytic in nature. The original proof was given by de la Vallière-Poisson independently by Jacques Adamard, and it was modified by Ingham, and it uses the Riemann-Lebesgue lemma. A second proof similar to but simpler than the above makes use of the Wiener-Ikehara theorem in place of the Riemann-Lebesgue lemma. And the proof of this Wiener-Ikehara theorem, I'm going to state it, but I'm not going to prove it. You can find it in books. It's quite technical, and I'm not going to go through that one. There is an analytic proof due to Newman, 1980, and I might go through that at the very end of this. So all analytic proofs, all analytic versions of the proof require some kind of Tauberian theorem from measure theory in the final step. So either the Wiener-Ikehara theorem, the Riemann-Lebesgue lemma, or in the case of Newman, he uses a thing called the analytic theorem, we might look at later. So, as often in what happens in mathematics, we try and write the given problem in terms of an equivalent problem, and then we solve the latter. So this equivalent problem is going to involve the function psi of x, which we're going to define, and this is the partial sum of the von Mangold functions. So we introduce these so-called Chebyshev functions, these famous functions psi and theta. So psi of x are the partial sums, as I said, of the von Mangold function. So it's the sigma of lambda of n for n less or equal to x for x positive, where this lambda of x is the von Mangold function, which you will recall takes the value 0 unless you hit a power of a prime, and in which case you then take the log of that prime. So capital lambda of x is 0 unless n is of this shape, and then it takes the value log p. So noting that lambda of n is 0 unless n is a prime power, we can get some other expressions for this. So here's our definition of the psi of x, and what we're going to do is we're going to then take capital lambda of p of m, where we look at all the prime powers less than x, because this is 0 otherwise, and then we let m be the power of the prime going from 1 to infinity. Now of course this is only a finite sum, because once p to the m exceeds x, this will be 0. There won't be any term here. and that's equivalent to saying p less or equal to x to the 1 over m log p, because the log of, if you've got a prime power, von Mangold of p to the m is just log p. So this sum on m, as I said, is in fact finite, since it's empty if m is bigger than log of x to the base 2. And so we can rewrite this as the sum m less or equal to log base 2 of x, sum over p less than x to the 1 on m log p. So in this expression here, this inner sum here looks interesting. It's the sort of sums of logs of primes. It looks interesting in its own right, and so we're going to define then this theta of x for x bigger than 0 by the sum of log p, p less or equal to x, where of course p is a prime. So this theta of x is just the sum of the logarithms of the primes less or equal to x. So these two very important functions, and we're going to see that they're very intimately connected, and also see that they're intimately connected with the prime number theorem. So that, as I mentioned, that sum is taken over all primes p less or equal to x. Now that means we can now go back and rewrite our psi of x. We can write that now as the sum of m less or equal to log of x to the base 2, and then theta x to the 1 over m. Now that's worth writing out in a little bit of detail to see what this is then. So this psi of x is then theta of x plus theta of x to the half plus and so on up to theta of x to the 1 over m, where 2 to the m is less or equal to x. Now our first little lemma that connects these two is that if you subtract psi of x on x minus theta of x on x, then it's non-negative, and it's got a bound above by log of x all squared on 2 root x log 2. Now before I have a look at the proof of that, that is very interesting, because we see then as x becomes very large, then this term will go to 0, albeit slowly, but the root x on the bottom will dominate, so this will go to 0 as x becomes very large. And that says for x very large, these two functions are very close to each other, psi x on x and theta of x on x. However, let's just have a quick look at the, in fact I'm going to do two things. I'm going to do just an example firstly of the psi, and then we'll look at the proof of the lemma. So here's a little example here. If we want psi of 10, so psi of 10 is the sum m equals 1 to 3, p to the m is less than 10 log p. So we can take p is the prime 2, and then 3, and 5, and then 7. So that's when m is 1. And then when m is 2, we want p squared less than 10. Yes, 2 squared is less than 10, so we take a log 2. And 3 squared is less than 10. Yes, so we take log 3. And then if we put m to be 3 in, 2 cubed is 8, which is less than 10, so we take log 2. And once we get beyond there, if we take 3, 3 cubed is bigger than 10, so there's no more terms. So we can simplify that. We get 3 log 2 plus 2 log 3 plus log 5 plus log 7, which is log 2620. So that's just a simple example of calculating what psi of 10 looks like. And theta of 10, well, that's just the sum of the primes less than the sum of the logs of the primes less than or equal to 10. So that's just log 2 plus log 3 plus log 5 plus log 7. And that's just log 210, if I'm not mistaken. So that's log 210. Okay, so our lemma then was that if x is positive, then we have this nice inequality that psi of x minus theta of x is non-negative, and it's bounded above by this expression here. And here's the proof. So we start off with this version of psi of x, which we saw was equal to the sum m less or equal to log of x to the base 2, theta of x to the 1 on m. And now I'm going to, of course, subtract these two. So if I take psi of x minus theta of x, then I'm just going to be looking then at the sum of this expression, but we're going to exclude m is 1. Yep, we're excluding m is 1 because that's taken care of by this thing. So theta of x then is the sum over the primes less or equal to x. So sum of the log of the primes less or equal to x. Now we can get a very rough approximation. We can just replace p with an x and say this is the sum of log of x for the primes less or equal to x, which is just, of course, less or equal to x log x. So pretty rough approximations there at the moment. So we plug this into here. We then have this difference between the two is less or equal to that from the previous line that we had. We're just replacing this theta of x with x log x. So x log x to the power of 1 over m gives me this. And then again, this is independent here, so I can just say this is equal to log 2. There are going to be log 2 terms roughly here, multiplied by each of these. And taking the smallest one, and then rearranging this. This, of course, is log to the base 2. So I turn this back into logs to the base e, and we get this expression here. So you can check the calculations there. So be careful with our logs. This is log to the base e, of course, and this is log to the base 2. So we have to change everything to log to the base 2. So log to the base e, I should say. So I've just got the root x, you bring the half down the front and then change base. Finally then, when I then divide everything by x, I have the desired inequality. When I divide by x, the root x on x will give me a root x in the denominator. So there is a little proof of that equivalence. Now the point about this is then, and this was realized, I think, by Chebyshev, that this now gives me this equivalence that the limit of theta x on x is 1 if and only if the limit is psi x on x is 1, because as we mentioned, as x becomes very large, this term here is going to 0. So for x very large, the limits of these as x goes to infinity are going to be the same. Now the problem is, of course, and this is the key point here, this assuming that each of these limits exists in the first place, because these are complicated functions defined in terms of primes, and we don't know that either of these limits actually exist. It just says if they do exist, then their values are equal. So that's the subtlety there. And we're going to see that each of these two statements in themselves are equivalent to the prime number theorem. So to do that, we're going to have a number of statements equivalent to the prime number theorem. So a sequence of statements that will get us from the prime number theorem back to here, and then we'll aim to prove, we'll aim to prove this result. Newman's proof, in fact, works on this one, interestingly, but almost all the other analytic theorems operate on this function here. Well, to do that, we're going to need some more technical results. We need a thing called Arbel's identity, which is a nice little way of doing summation involving integration again. So we have a of n as any arithmetic function, and capital A of x are the partial sums of my arithmetic function, where again we're going to take a of x to be 0 if x is less than 1. We're going to take f to be a C1 function on the interval yx, where y is between 0 and x, and then the Arbel summation formula says that we can take the sum for n strictly bigger than y, less or equal to x, of this arithmetic sequence multiplied by any C1 function is equal to the product of the partial sums times my function at x minus the partial sum of the partial sums plus times f of y at y, minus this integral of a of t times f dashed of t. Now I'm going to prove a slightly easier version. I'm going to put y to be 0 just to make life a bit easier here. You can do it more generally, but I'll just put y to be 0, save fiddling around too much. And I'm going to put k to be the floor of x. Then we do our usual idea here. We're going to write the sequence as the difference between two of the partial sums. So the an term is just the sum of the first n terms minus the sum of the first n minus 1 terms, and I'm going to split that into 2 bits. And in the second bit we're going to change variable. I'm going to replace n minus 1 with n. Replacing n minus 1 with n gives me this sum. I take off the last term, so I get ak fk, and I get the sum then of this difference. And so at the next stage then I can now write this as I can write this difference here as just the integral of the derivative, because if you integrate that, put in the endpoints and subtract, you get this. Copy that down, and we've still got our sum there. Noting here that a of 0 is 0. So I've added in 0 here, but of course I'm not adding in any, that extra term's going to give me 0 here. Finally then I can write that last expression as minus. I can now take this, I can now take the sum of these integrals and take this term inside. So I now get the integral from minus 0 to kat f dash of t plus this last one. And finally then, writing down what we've got, this sum that we started with is then replacing the k with the x, because k was the floor of x. We get a of x, f of x minus this integral, and that is the version with of the Arbol summation formula with y to be 0. Now using this technical piece of mathematics, we can express the Chebyshev function theta of x in terms of an integral, and we can then relate the integral back to the function pi of x, which is our desired aim to get our hands on this integral, on this pi of x, the number of primes less or equal to x. And the way we do this is our next theorem, theorem 6.2. So here's our two formulae here. Theta of x is equal to pi of x log x minus this integral, which is the integral from 0 to 2 up to x pi of t over t dt. And alternatively, we can also write pi of x in terms of theta of x, and so pi of x is theta of x on log x plus this integral. Now, there are various ways of writing these things. You can do this using Stieltjes integration notation. I haven't done that. I've just used ordinary integration techniques. Remembering that these things, of course, are step functions, but that's okay. This still makes sense on a finite interval. So here's the proof of the first one. We're going to take this sequence a of n is 1, so this is a prime counter. It's 1 if n is prime, 0 otherwise, and then pi of x, of course, is just the sum of 1 if counting over the primes less or equal to x, and I can write that using my new sequence here. Theta of x is by definition the log of the primes less or equal to x, and again I can write that as a of n log n, because this will be 0 unless n turns out to be a prime. So this enables me, this an function enables me to go from a sum over primes to a sum over just the natural numbers. Now I'm going to apply Arbel's identity with a of x is pi of x, f of x is log x, and y equals 1. And as soon as you plug that in, you get immediately part A of the theorem, because you get pi of x times log x minus the integral of the partial sums, which are pi of x, times the derivative of log x, which is 1 over x, and then you're replacing x with t, and that's, you get exactly the formula up here. So that was just a straight application. That falls out immediately from the Arbol summation formula. For part B, a little bit more fiddly. We now take the sequence b of n as this a of n we had above, times log n. And then pi of x then we can write in this form, because the b of n, it's just this pi of x is just the sum of 1 over the primes, which is the sum of an over the natural numbers, and the logs cancel out. So we can write this in this form, and theta of x we can write as this one, because again it's just log p, so this is 0 unless n is a prime. So we can rewrite these in terms of this new sequence bn. We take f of x to be 1 over log x, and we're going to use y as 3/2. The partial sums are going to give me my theta of x, which we saw here, and we now apply Arbel's identity again, and we just plug that in. We get pi of x is theta of x on log x, minus theta of 3/2, this is the theta of y on log of y, and then we have to differentiate this, which is going to give me y minus 1 over t log t squared, and then that's what we get when we plug it into Arbel's summation, Arbel's identity. And I've just simplified here. This is 0, copy that down, and there it is. And we can replace the 3/2 with a 2, because this is 0 until we hit the 2 there. So theta of t is 0 if t is less than 2. So here are our two formulae, and in the next section we're going to prove this following result here, which I'll just state here, and we'll come back to this in a moment. But we can now get some equivalent formulae for the prime number theorem. It says that pi x times log x on x goes to 1, which is the prime number theorem. If that limit exists and equals 1, then this limit exists and equals 1, and that limit exists and equals 1. So these are all if and only if expressions here, and we'll continue that with the next recording.